All right, so we're going to cover the second part of this chapter, and it's a little bit different than the first part, but the initial parts are about the same. We're going to look at acid-base calculations for mixtures of acids and then for polyprotic acids. And then what we're going to do is we're going to look at how the structure of a molecule affects its acid-base properties. And this is one of those things that while it may not seem that important here, it becomes really important as we get closer to organic chemistry and you start thinking about things in terms of reactions like organic reactions where the acid-base properties all turn out to be super important. All right, so let's get going here. We're going to do this example. We're going to calculate a pH when you have a mixture. Now, this one says weak acid and a strong acid. But it could be a weak acid and a weaker acid, for example, or a weak base and a weaker base, that kind of thing. And the general rule is always the same. The stronger acid you calculate first, and then you calculate for the weaker acid, okay? Now, the reason we do this one is because it's easier to explain it first. So let's say you have a strong acid and you put it in water and you wanted to calculate the pH, right? Well, all you need to do at that point is you say, well, to calculate the pH, I assume it's 100% ionized, and then I say negative log of the concentration, and if it's an acid, that gives you the pH, and if it's a base, it gives you the pOH. So process is, if it's just an acid, then you're going to go complete ionization, and then molarity equals concentration of hydronium for the acid, or base, OH for the base, and then you just calculate pH. So that problem is pretty straightforward, but for, let's say, a weak acid and a strong acid, this is what you do. You assume the strong acid reacts first, even though they're both really happening at the same time, and you go ahead and say the hydronium at the beginning is what the concentration of the acid is at the it's what the concentration of the hydronium is at the beginning of an ice table, because you assume it just ionizes automatically. And then the acetate, this is supposed to be acetate, so get rid of this. This is supposed to be 0. And in this problem, we have 0.10 molar acetic acid. And then we, again, ignore this, and we're going to say minus X, X, and X. So you see this problem is very similar to the ones we've done before, except now we have some hydronium initially present. And so we'll have to set up a Ka expression. Ka is going to look like 0.010 plus X times X divided by divided by, I brought up a menu, 0.10, I don't know what happened to that 0, minus X, like this. And then that's equal to the equilibrium constant, 1.75 times 10 to the minus fifth. Now, in this instance, the hydronium is what is known as a common ion. I have hydronium in the solution already, so it's going to suppress the ionization of the acetic acid. What I'm going to do to solve this problem is assume that X is small. Now, if I'm going to assume X is small, and then we'll do the solver problem. I'll show you the answer from the solver. But if I assume X is small, what happens? Well, for sure, I can ignore it down here. I mean, that's what we normally do anyways. So I'm going to eliminate this value. But see, I can't X out an X, so I'll just do that. And then I can also eliminate this value because I'm assuming X is small. So then what I'm going to do is I'm going to calculate. I'm going to say, okay, pH, hydronium, get back to my black just to keep my colors right. Then what happens is I have 0, this is equal to 0, I'm just rewriting, 0.10 times X over 0.10 like this, and it's equal to 1.75 times 10 to the minus fifth. Now what I need to do is rearrange this, and that's going to come out to be that X is equal to 1.75 times 10 to the minus fourth molar. Okay, so then the question is, what's the pH, right? And this is where people will make mistakes in these problems. They go ahead and they just say negative log of this value. But the hydronium is all of this. And again, notice this value here is 1 times 10 to the minus 2. This value that's down here is basically 1.75 times 10 to the minus 4. So x is actually small. I validated my assumption by looking at the value of x compared to this. Okay. So now what I can do is calculate my pH. pH is going to be negative log of, and then it's going to be 0.010 plus my x value, like that. So I ended up with 1.992 for my pH. Now you have to remember I only have 2 sig figs, so I would round it there, so it would be 1.99. And just to show you this, let me switch over. I actually solved that on a calculator. So x, it turns out to be, if you use a solver, you can get an x value 1.717 instead, times 10 to the minus 4, instead of 1.75. So it's only different in this third place here. Now, when I calculate the pH for this, so this is the approximation, and this is the solver. The pH comes out to be, right, 1.993. And so again, rounding to 2 significant figures, I end up with an answer of 1.99. So you didn't see me do all the extra work in the background, but I entered the equation in and all the values, and I did set this to 0, and then I did the alpha solve. And again, if you have this kind of calculator, or if you have the TI-36X Pro, solvers generally work the same way. You would get this answer, which is more exact than the approximate answer. But remember how we got the approximate answer? We just rearranged what we had over here, and then we were able to get this answer pretty quick. So it did save a lot of work to use the approximate answer in this. Now, think about what happened, though. See how small this number is relative to this number. The degree of ionization is going to be small for weak acids, and it's even smaller when a common ion is present. So all the hydronium that makes up the pH of the solution really comes from the stronger acid. So when you have a strong acid and a weak acid, the pH really can almost always be calculated from the strong acid. Now, if you're not sure, you set up the ice table, you check you run the calculation like we did here, and then you check. So the next thing that we'll do is look at what happens when we have a mixture of a weak acid and a weaker acid. Okay, so we'll use acetic acid maybe and like nicotinic acid in a mixture, and then we'll calculate what the pH is. So what we're going to do next is we're going to tackle a problem that has 2 weak acids where one's stronger than the other. And then after I'm finished with this, I'll talk a little bit about like how this problem solution method has its flaws. But we'll go ahead and follow the process just like we did for a strong acid and a weak acid. We'll just take the stronger acid and we'll calculate the hydronium ion from the stronger acids first. And so what I'm going to do is assume that X is small for this first one. And so I'm going to go, well, then hydronium concentration is equal to the square root of Ka times C. And that's going to be the square root of 0.10 times 1.78 times 10 to the minus fifth. Now I do this for the strong acid first because we're going to assume that the strong acid, because it's stronger, will dominate the equilibrium mixture with its hydronium. So when we do the calculation, we get a concentration of hydronium of 0.00132, and I'm going to carry a couple of extra digits here, like that. But again, this particular Ka has 3, so we'll go there, 3 significant figures, and that's in units of molarity. Now what I need to do is set up an ice table for the weaker acid, and I'm going to use HAC. This is for acetic acid. AC is actually a common abbreviation. And then I use Nic for nicotinic acid. And then we have plus H2O. And that'll make hydronium. And I'll give myself a little more room here. Plus Nic minus, like that. So I have an initial set of conditions, which HAC, acetic acid, is 0.10 molar. I'm going to ignore the water. The hydronium will start now at 0.0013223, and the nicotinate ion is going to be 0. And then we have the change, and we have the equilibrium. And then this is going to be minus x, be plus x, and plus x. And so we sort of follow the same format that you're familiar with. We're going to have 0.10 minus x, and then I'm going to have 0.0013223 plus x, sorry about that, and x. So Ka follows the same form. Sorry, I got something there. It follows Ka for the nicotinic acid will be the concentration of hydronium times the concentration of the nicotinate ion divided by nicotinic acid concentration, like this. Okay, and then I just plug in those values. So I'll end up with, in parentheses, 0.0013223 plus x times x divided by 0.1 minus x. Now, you can look at this problem and think you might be able to just throw all those x's out like we did before, but the problem with this is this concentration is very small. So you can do a x is small approximation for 0.1, but you can't do it for 0.0013223. So instead of doing that, I just threw it into a solver, and then I get the concentration of, or the value for x being equal to 0. I was saying, let me do it like in scientific notation. So it's 8.129 times 10 to the minus 4th molar, like that. Now, you can't calculate pH from this value of x because pH depends on all the hydronium, and we assumed some came from this value here. So now what I have to do is take my value of x in here, and then if I do that, my concentration for hydronium ends up being 2.135 times 10 to the minus 3rd molar, and it gives me a pH equal to 2.67. Now, so some of the things that we did in this problem, just go back to review, and I'll talk a little bit why this is a little bit of a hazardous way to do these problems, is that we assumed the stronger acid ionized first, and that's a fair assumption to make. And we did X's small approximation and got the first value for hydronium, and we plugged it in here. And then we did the same thing for the acetic acid. We said, started a table assuming the ionization of acetic acid. We started with this concentration, but now the hydronium, we're assuming that there's hydronium already present from the ionization of the nicotinic acid. And so we have to set up our ice table like this. We plugged in our expressions from the equilibrium line. We solved for x, and then this value is not the total hydronium. This value is. And so I have to add those things together, and then I get the molarity and I calculate the pH. So let me talk to you a little bit why this is a problem. But first, let me just tell you what the answer is, like what if you do this problem exactly the right way, how the pH comes out. And if you do it exactly the right way, It comes out to be 2.72. It's not that different, okay? But in real careful work, people take these things into account. And here's the problem. What we're doing is we're assuming that the ionization of the nicotinic acid happens independently of the acetic acid. But in really what happens in solution is both of these are ionizing at the same time, and they're producing a common ion that's hydronium for both of them. So in a sense, they're both producing hydronium and then suppressing each other's reactions, and so you don't produce as much hydronium in the solution as you would expect. Okay, so there's an interaction. I have HAC, and that's producing H3O plus. I have HNic, which is also producing H3O plus. This is the common ion. And because they have that common ion effect, they ionize less. What does that mean about pH? Well, it'll be a little bit less acidic because the ionization is being suppressed for both. And when you look at the pH for the exact solution, it's a little bit higher than the pH for the independent ionizations. And this is generally true when you have multiple equilibria in solution. There's actually a more precise way of solving these. If you're interested, I can show you the solution, but it involves like pages of equations. But I just wanted you to know there is a better solution out there. But for most things that we do, this kind of solution works out pretty good. It's not that different. And if the Ka values or the concentrations are dramatically different, then this kind of solution actually works pretty good. Okay? So that was an example. We've already done an example of a strong acid and a weak acid. And then we did a weak acid and a weak acid. And then showed this is really the worst case scenario for this approximation. All the other approximations would come out closer, the types of problems that you're going to see in the book.